graduate program on analyzing the connections between nonlinear filtering and statistical physics.
Let me make some philosophical remarks. So my main background is control and broadly defined. And it seems to me that the questions that were asked in control theory, I would say maybe 20, 30 years ago, although often worked out in the context of linear systems, but the questions that were asked, I think, are still relevant. And my sense is that there's too much emphasis is going on machine learning and not enough on sort of structural and modeling questions. And I want to suggest some of those things. So that's one. The second thing is that I think if these ideas are going to be relevant in biology, by biology I mean, say, brain modeling in some sense, then one has to be sensitive to, for example, be concerned about issues of communication and theories of communication or theories of information that may be relevant. It has to take into account the fact that communication, I think in brain modeling, is purposeful in the sense that you communicate in order to execute certain desirable actions. So I think one has to come to grips with theories of information and theories of control, because information theory, Shannon information theory, as it stands today, is and really an infinite delay situation. It's like passing to the thermodynamic limit. And if control is important, then you have to worry about delays and issues of stability. So a lot of my work has been trying to relate information theory and theories of stochastic control, for example, and how those theories may be modified. Now, there are other things, like there's an old paper by Jerry Ledwin and his colleagues, all at MIT, and the paper is called What the Frog's Eye Tells the Frog's Brain. And I think the important message there towards the end of the paper is to say that the frog's eye communicates with the frog's brain in very abstract terms. What that means is that it's not that the images are represented by some large covariance matrix or something like that, but in terms of structural components, like perhaps number of connected components, or more generally invariance, topological invariance of one kind or another. Lastly, I think physicists are definitely interested in bringing information theory and statistical mechanics together. There's rather interesting work. And that work is I think, relevant and interesting, and one should pay attention to that. Okay, so today I'm going to talk about stochastic control in some broad sense of the term. Stochastic control with imperfect observation, which I would say is the sort of the parent theory of reinforcement learning. So this is all in continuous time. I think the results that come out are more revealing in continuous time than in discrete time. And I want to relate some of the work on variational principles to, for example, ideas of the neuroscientist Carl Friston, who has suggested that free energy minimization is a unifying principle in the way the brain keeps equilibrium with its environment. That is a unifying principle. Okay, so lastly, I think many of the algorithmic work that's going on in neural networks and optimization perhaps can be illuminated by sort of lifting everything to the space of measures and understand that those algorithms as dynamical systems as the dynamics of the space of densities rather than as discrete time algorithms. Okay, so those are some of the philosophical principles. And I think old ideas of issues of proving convergence by looking at the corresponding differential equation proving stability also may be a technique that could be useful. Oh, is the thing on?
This button. I just pressed it.
Okay, so this is what I've spoken about. Okay. What this slide shows is the idea of directed information, namely if you have a sequence of random variables, then you have to, in the definition of mutual information, you have to take into fact that it's causal. So you condition really only on the past, as opposed to conditioning the whole sequence itself. That's this idea of directed information. Now, I want to discuss this nonlinear circuit with a nonlinear resistor, and one of the ideas is that you make noisy measurements of the voltage. Let's see. You make a noisy measurement of the voltage, and you're allowed to inject current into this nonlinear circuit. And the idea is that, for example, one of the questions you could ask is, how much work can you generate it from this noisy circuit by injecting current into this circuit? And that's an optimal control problem. And the interesting result is that the amount of work that you can generate depends on your measurement, this measurement across the capacitor to the control, to the feedback control system. And the amount of work can be computed, and it is the directed information from the measurements to the control. So this, if you like, the thermodynamics of this noisy circuit is intimately related to some information theoretic quantity. So this is a paper of mine in PhysRev where this is worked out. I guess I should master this. Which one? It should be this, right? Okay. Now I want to give a simple account of the Gibbs variational principle. So this is given sort of two random variables, x and y. This average dependence of x and y can be defined in terms of the mutual information, which is the log of the joint distribution divided by the product distribution. And that is a special case of definition of a relative entropy of Kullback-Leibler information between mu and nu. So this, I mean, in the more general case, this would be log of the Radon-Nikodym derivative between mu and nu, an expectation over mu. So it's an average measure of average dependence between two random variables. Okay, and the properties are that it's non-negative. It's the distance, it's the pseudo distance. It's equal to 0 if mu equals nu, and h of mu nu is jointly convex. Now, this is a conceptual point that we want to think about descriptions of systems which are described by stochastic differential equation. So, fed by so-called white noise. And that's just a formal way of writing this rigorously in terms of its integral, where this integral has a special meaning. So we would want to think about random variables in general terms, that a full trajectory will be a map from some probability space, say, for example, the space of continuous functions. Now, there's another idea which is important, that you can look at these trajectories as sort of a local description, which is the solution of the stochastic differential equation for every omega. Or you can fix the trajectories and look at it under some different measure, where, for example, under the different measure, these trajectories could be viewed as trajectories of Brownian motion. So there's an important change of measure argument. Okay, now I want to quickly describe Gibbs measures, because one of the results I would want to get is that there are many inference ideas are related to the Gibbs variation principle. So I'm going to quickly do that. So this is in the finite case. So S is a finite set and E is the state space, and omega is function from S to E. And you define a Hamiltonian H, which is the sum of these potentials. So the notation phi A is phi restricted to the subset A in S. And the definition of Gibbs measure Gibbs measure is exponential of much of omega normalized. That's the so-called partition function. And so the notation is mu h is really integral of h d mu. So that's the average energy, and lowercase h mu is the entropy. And what you can, this is everything is discrete. So if you look at the average energy minus the entropy, that's plus log of z, z is the partition function. If you do a computation, that's just the relative entropy between mu and nu, and is non-negative, and h of mu and nu equal to 0. And when mu is equal to nu, the Gibbs measure. And the so-called free energy is the average energy minus the entropy. And what you can, sorry, that's, right. And the so-called free energy is just from this expression from mu h minus h of mu plus log z. And that is non-negative. That the so-called free energy is minus the logarithm of the partition function. That's the amount of energy available to you to do work. Now, it turns out that the infinite version of that is the so-called Gibbs variation principle. And one can show that the noisy channel coding theorem, at least the noisy channel coding theorem is the theorem in communication theory given by Shannon, that if you transmit information at a rate which is below the capacity of the channel, and capacity is the definition in terms of the mutual information, then there is a way of coding and decoding the information so that the message can be transmitted, at least if you allow enough delay, without any error. And if you transmit at a rate above capacity, so you cannot. So that theorem can be proved as a theorem involving sort of Bayesian inference. And this is in my paper with Nigel. Okay, so what I now want to describe is nonlinear filtering problem. And so the filtering problem is that you're given so they're different. So you have a nonlinear dynamical system fed by white noise, right? That's the canonical model. And associated with the stochastic differential equation, right, there's a second order differential operator, right, which is the operator A. And so here, I should be I've done, I think I switched it off. Do you know how to make it back?
I think it's working. This big one is the pointer, and that's forward and back.
So what this result says is that associated with that nonlinear stochastic dynamical system, there's a concept of free energy. And minimization, free energy corresponds to thermodynamic equilibrium, which I showed you in the discrete case before that. So this is what it says, that if PSS is the unique invariant measure with density P of S, the entropy of the closed system is maximized by P of S and non-decreasing. Now, my goal is that if I define now, I allow observation. So y of t is some nonlinear function of the state x of s plus white noise. So this is just a continuous version of a signal plus noise model. And then the main idea is that what you're looking for is really the conditional distribution of x at time t given observation, sequence of observations ys between 0 to t. So you can write down an evolution of the conditional density, if you like, which is equation 2 here. Now this equation is interesting in the following sense. So what the conditional density is doing is it creates a model of the system. That's this part of the filter. Based on this model, it makes a prediction. So the notation is that this is integral of the conditional density with respect to G. It creates a model of the system itself and makes a prediction of the output G based on that model, and then some new information comes in and you make a correction with an appropriate feedback. So the interesting thing is that the structure of the filter as a model and a predictor is completely embodied in this equation itself. And mu of t is, so this is the new information. This is the new information at time t, and this is the prediction of the signal g as a best estimate, right? This is the integral of g with respect to the conditional density. So what I'm interested in is, so the interesting point is that the theory gives you the structure of the filter itself. So although you might computationally, for example, in the discrete case, this is some sort of belief propagation, but this is a theory. The theory gives you a structure of the filter itself. That's the important point. And the point is that what I want to do is to introduce ideas of information into the filter itself. The filter is some kind of an algorithm with a structure. So the question that you ask is, what exactly does the filter do in an information theory sense? Namely, how does information flow through the system itself? And so, for example, is this flow conservative or dissipated? Okay, so here is one of the main results. So S of t is the mutual information between the trajectories. Okay. So what S of t is, so you have to imagine the following. There's information contained in the observation, and that information coming in dynamically into the filter itself. The filter then stores that information that is needed to understand the present or the future. Then there's some leftover information that is not useful for predicting the state x at time t. However, if you wanted to compute the whole trajectory itself, then you would need that information. Now, what the remainder is, namely this d of t, which is a mutual information expression for it, is the information that is dissipated at an optimal rate. And this optimal rate is actually this dissipation, this optimal rate at which information is dissipated is actually the Fisher information. So the two lines of statistics, if you like, information theoretic and Fisher information. So this relates the mutual information with Fisher information. And then we can write down differential equations. So especially look at the equation for d dot of t. And that is the cumulative Fisher information. And you can ask the question of how does the probability density starting at time 0 to time t, how far does that travel? And that is measured by the Wasserstein distance between the initial state, conditional initial state, and the new state at time t. So embodied in this filter is also a relationship between the Wasserstein distance Shannon information and Fisher information. So just as you can do statistical mechanics, say, of or even non-equilibrium statistical mechanics of a noisy circuit, of a noisy system interacting with an environment, you can now do a conditional statistical mechanics, all based on where measurements are part of the system itself. Okay. So, sorry, you have to speak a little louder. Yeah, that is a Markov process itself. Between the initial state and the conditional density at the time t. So it measures the amount of time that the initial density has traveled up to time t. So this is related to the work of Kindler, Otto, and Jordan, where they do this for Fokker-Planck equation, but this could also be done for conditional density. So why might you be interested? I think the idea is to bring information theory directly into the computational process itself. So, for example, something that one would like to prove is what is the analog of the Max-Scott min-flow theorem, when what is traveling is not water but entropy itself. And I think if one could do that, you would perhaps make some dent into multi-user information theory. So, I mean, the philosophical issue here is that you want to bring together Also issues of resources, which is completely absent in information theory today, into the algorithm viewed as a dynamical system and study its properties. And this is one case where we can do it for the filter itself. Okay, now I want to say a few words about Bayesian inference viewed as free energy minimization and how that free energy interpretation has a stochastic control interpretation. Okay. Okay, here is the setup. There is a general probability space, omega fp, and you have two random variables, x and y. These x and y can take values in, for example, in a metric space, something like that. And then what this says is that P of x, the joint distribution P of xy, is absolutely continuous with respect to Px cross lambda y. Lambda y is some reference measure. You can take it as Py itself. And that, so this is essentially, if you look at the radical derivative of P of xy with respect to Px lambda y, that's just essentially the likelihood function. So that's what Q is. Now, look at this formula. So remember that in the finite case, if you minus log of z has all the statistical mechanical information that you need. So what this equation 7 says, that you can write down the conditional distribution P of xy as a Gibbs measure, where exponential of minus h of xy is, I mean, remember what h is. H is this radical derivative. Sorry, h is log of minus log of the radical derivative. So essentially, what this accomplishes is that it can be, the base formula pointwise can be written down as this expression on the right. So because you can write it down essentially as a Gibbs measure, you expect that this satisfies the variational principle. And what you can show is that if the px tilde is there's some prior measure on x, and px tilde is some other measure, and this is the relative entropy between the two. And I of h tilde is essentially it's really log of, it's a moment generating function, log of the moment generating function. And what you can now show is that this minus log of the moment generating function corresponding to h this has two parts. It is the minimum over this auxiliary measure px tilde, and the distance between px tilde of p of h, and h, remember, is minus the log of the likelihood function. That's the average likelihood function. what this formula shows is the duality between exponential moment generating function and the average energy. And there's a corresponding dual formula. So these two formula are really they are conjugate convex functions. So this theorem 1 is really an expression of differential duality between exponential moment generating function and average energy. And this is a special case of the Donskoy-Bardon variational principle, which arrives. So there is a beautiful interpretation between large deviation theory, differential duality theory. Now you assume that if X is a Markov process, then this equation I of Hy has an optimal control interpretation. And it turns out that the solution of this optimal control problem is actually a gradient flow. So there's a whole series of things. This is the Lejeune transform of each other. Stochastic gradient on space of measures, on space of density, and free energy minimization. And there are other problems like which Vivek is interested in, risk sensitive optimal control, which is related to these duality ideas. So in this slide, what is worked out are these stochastic differential equations, optimal control problem, and the necessary dynamics and the Hamilton-Jacobi equation. And so this circle of ideas should be relevant to understand stochastic gradient algorithm, for example. What I'm suggesting is that these ideas should have relevance to the analysis of neural networks as statistical mechanical systems. Okay, so there's a direct problem and an indirect problem. And that's again worked out in the slide. I'm happy to make the slides available. Okay, so I think I'll essentially stop here. What I've shown is that there's a close connection between Shannon information, namely mutual information, and Fisher information, and the Wasserstein distance. That's point one. Because there's a stochastic control interpretation of Bayesian inference, you can do so-called reinforcement learning. Bayes approximation scheme now is available in a rigorous way for Bayesian inference. 2. 3. We can study the ergodic behavior of these problems, namely the ergodic behavior of stochastic control problems. And this circle of ideas brings into play what one would want, information theory ideas directly at the algorithmic stage. Now there are many things to be done in this circle of ideas. Some of it is my other paper that a proof of so Shannon himself believed that when he understood information theory completely, it would look like thermodynamics. To some extent, we can carry out this program, at least for the direct part. direct part of the theorem. Namely, if you transmit at a rate below capacity, then you can recover the message error free. And that uses, by the way, the exchangeability ideas as replacement for stationarity. That's it.